The expansion of the universe has introduced several puzzling observations. I guess the first can be the accelerated expansion of the universe. That was discovered about 3 decades ago. And until now, obviously, we have some theories about it. There's no proven explanation to why that happens. Another one, maybe a little bit more recent, is the HO tension, the disagreement between the expansion rate when observed with galaxies and the redshift, and the expansion rate observed with the CMB. And that is a puzzling disagreement because we are supposed to have one universe that has one expansion rate. We're not supposed to have two different expansion rates. And another one is those mature galaxies that we observe in very high redshifts. Those galaxies are supposed to take billions of years to form, and we can observe them, let's say, a couple 100 million years after the beginning of expansion. So after we look at all of these things, we can suspect that all of them might lead to a single suspect, which is the redshift. But for some reason, the redshift is really getting a pass, and we don't really challenge the redshift. We challenge things like the theory of gravity, for instance, or we propose all sorts of exotic cosmological theories that in many cases they introduce more questions than answers. But the redshift is considered pure, is getting a pass. But it might be that if that single observation, single tool that we're using is biased, even in some of the ranges, not the entire range, that can explain all of those tensions in just a single observation. So that's what I'm going to do. That's what I'm doing here, and that's where I start. So that shows that's an experiment that shows that when comparing the average redshift of galaxies that rotate in the same direction relative to the Milky Way to the average redshift of galaxies that rotate in the opposite direction relative to the Milky Way, we see that they're not the same. They're different. The difference is statistically significant, and that's regardless of the sky surveys or the redshift survey that we're using, and it's very consistent in the north end of the galactic pole, the southwest end of the galactic pole. Both are showing the same thing. And that is something that's not expected. The redshift should be the same or very close to be the same, regardless of the direction of rotation of the galaxy compared to the Milky Way. But empirically, it's not, and that might seem surprising. And if you think it is surprising, then you can go to access all these data. So all data are publicly available, and the links are in the paper in the bottom part of the slide. You can see that paper. Go to that paper. In that paper, you have URLs to all of these data sets are publicly available. You can go check that the data are clean, consistent, that the results are the same the results as shown here. Just make sure that everything is in place. And here's some data sets that are not by me. They're third-party data sets collected by other people, released by other people. And again, they show exactly the same thing. They're not as big as my data sets. I think they're not as clean, but they still show the same thing. And these are data sets that I didn't even touch. So, and everything is leading to the same observation, same conclusion. Again, those data sets are also publicly available, just like my data sets. You can go check them, see what they do. And here's new data from DESI DR1. So DESI provides obviously a lot more spectroscopic object than other spectroscopy survey. And here we have over 13,000 galaxies, and we separate them to galaxies that rotate in the same direction, galaxies rotate in the opposite direction relative to the Milky Way, and they're all very close to the galactic pole. So we have a relatively large number of galaxies on the galactic pole. We see the same thing, that we see the same redshift difference as we saw before. So we see the same thing, just with more galaxies. And the statistical significance is very low. Unlike the other data set, this data set is not yet publicly available. I have not published that paper yet. That's the reason why it's not publicly available. I have not even submitted the paper, still working on it. So if you want the data, to access the data, you can contact me. It's not yet publicly available like the other datasets. That's where it gets maybe a little bit more interesting. So what's here is the separation of the data into redshift ranges. And what we can see is that the bias in the low redshift ranges is very close to zero. There's hardly any bias there and on the low redshift. But when we get to the high redshift, as the redshift gets higher, the bias also becomes stronger. So when we get to the 0.3 redshift, then the bias is much higher. And we can see that both the south pole and the north end of the galactic pole, the green is the south and the purple is the north end of the galactic pole. We see that, again, fairly consistent. So they're not exactly the same. There's some statistical fluctuations here, but again, very consistent between the two ends of the galactic pole. So if that trend continues, I don't have data beyond redshift of 0.3, but if that trend continues, it shows that the bias is increased in the higher redshift ranges. But that's also where we see those problems. Those mature objects, we see them in the high redshift, and the HO tension exhibits itself with galaxies with the higher redshift ranges. When we only use galaxies with low redshift, we don't have an HO tension. So if that trend continues, that can explain that. And that's the same, very similar experiment, but with HSC data and spectroscopy from SDSS. So maybe the data set is not as good as DESI, but it still shows the same thing. And we have also the south galactic pole, the green line, the north end of the galactic pole, the purple line. And again, very consistent. It's consistent across both ends of the galactic pole, and increases the bias. We can see increases with the redshift. And that data set is publicly available. You can look up the paper that is specified, listed here in the bottom of the slide, and you have a URL there. You can access the data, make sure that it's clean, it's consistent, make sure the results are what you see here, and maybe try your own experiments with it. The data should be pretty solid. And how do we make a direct connection between that and the HO tension? So here is a simple experiment that shows data set of supernova. So what I did here, I separated data set into galaxies that rotate in the same direction relative to the Milky Way and in the opposite direction relative to the Milky Way. When computing the HO just with galaxies that rotate in the opposite direction, in the same direction relative to the Milky Way, then the Hubble tension almost disappears. It reduced substantially and basically disappears. When using galaxies that rotate in the opposite direction relative to the Milky Way, the Hubble tension increases. It becomes more substantial. I have to say that these results are not statistically significant because after sorting those galaxies, you left out with a small number of galaxies, some small number of supernovae and galaxies. So these results are not statistically significant. More work is needed here. If you want to do an experiment with a higher number of galaxies, a higher number of supernovae, then I'll be happy to help you to do that. And the reasons can be either it's indeed that the redshift is indeed biased, and that can explain the other observation that we have or the other tensions that we have. Another possibility is that the redshift is still correct, and what we see here is some anomaly in the large-scale structure of the universe. Those galaxies are indeed closer to us, maybe, for some reason that it's difficult to explain, and at this point, and it also, the peak coincides with the galactic pole. So the alignment with the galactic pole could be a coincidence and not because of the motion of the Earth within our galaxy. So thank you for listening.